Most people think resistance explained is a material that uses up electricity. But in engineering, this is not correct. In this video, we will understand resistance explained clearly from the fundamental level. Resistance is the property of a material that opposes the flow of electric current. It does not consume electricity, but it limits how easily electric charge can move through a conductor. Inside a conductor, free electrons move through a lattice of atoms. As they travel, they constantly collide with atoms and other imperfections in the material. These collisions slow down the overall drift of electrons, reducing current flow. The amount of resistance depends on the material type, its physical dimensions, and temperature. For example, copper has very low resistance, which is why it is widely used for electrical wiring. In contrast, materials like rubber have very high resistance and are used as insulators. Resistance is measured in ohms, omega. 1 ohm represents a specific relationship between voltage and current in a circuit. So, resistance is not a substance or energy loss itself, but a physical property that describes how strongly a material resists charge movement. First, when a voltage is applied across a conductor, an electric field is created. This field pushes free electrons to move in a specific direction, creating current. However, electrons do not move freely without interruption. As they travel through the atomic lattice, they collide with vibrating atoms. These vibrations increase with temperature, making collisions more frequent. Each collision reduces the momentum of electrons, effectively slowing down their drift velocity. This reduction in motion is what we perceive as resistance. Different materials have different atomic structures. In metals like copper, atoms are arranged in an ordered lattice that allows relatively smooth electron movement. In contrast, materials with irregular structures cause more frequent collisions, resulting in higher resistance. As a result, resistance determines how much current can flow for a given voltage. Higher resistance means fewer electrons can drift through the material in a given time. Thus, resistance is fundamentally a microscopic interaction between moving electrons and the atomic structure of a material. A simple way to understand resistance is to imagine walking through a crowded hallway. If the hallway is empty, you can walk quickly without any obstacles. This represents a low-resistance material like copper. Now imagine the same hallway filled with many people moving in random directions. You can still move forward, but you will frequently bump into others and slow down. This represents a material with higher resistance. The more crowded and chaotic the environment, the harder it becomes to move efficiently from one side to the other. In the same way, electrons moving through a conductor experience collisions with atoms inside the material. These collisions slow their overall progress. Resistance is therefore not something that actively uses up electricity, but rather a measure of how difficult it is for electrons to move through a material. This is why thin wires, long wires, or poor conducting materials all increase resistance and reduce current flow in a circuit. In electrical engineering, resistance is a fundamental parameter used to control current flow in circuits. It is used intentionally to limit current, divide voltage, and protect sensitive components. Resistors are designed components that provide a specific and predictable amount of resistance. By selecting the correct resistance value, engineers can control how much current flows in different parts of a circuit. For example, LEDs require resistors to prevent excessive current that could damage them. Voltage divider circuits use resistors to produce specific voltage levels from a higher supply voltage. Resistance also plays a key role in power dissipation. When current flows through a resistor, electrical energy is converted into heat. This is why resistors can become warm during operation. Engineers must carefully consider resistance in all designs because it directly affects efficiency, stability, and thermal performance of electronic systems. In RF systems, resistance becomes more complex because current is not constant but oscillates at high frequencies. At these frequencies, additional effects, such as skin effect and parasitic resistance, become important. Skin effect causes current to concentrate near the surface of conductors, effectively increasing resistance at higher frequencies. This changes how signals propagate through transmission lines. Resistance in RF circuits also contributes to signal loss. As electromagnetic waves travel through conductors, some energy is converted into heat due to resistive effects. Engineers must carefully minimize unwanted resistance in RF designs to maintain signal integrity and efficiency. This is especially important in antennas, transmission lines, and high-frequency circuits. At the same time, controlled resistance is also used for impedance matching, which ensures maximum power transfer between components in RF systems. Thus, resistance is not just a loss mechanism, but also an essential design parameter in high-frequency communication systems. So today, we learned that resistance is the property of a material that opposes the flow of electric current, not something that consumes electricity. We went from definition mechanism, intuition, engineering, view, RF application, to build a complete understanding of the concept. This foundation is essential for the next topic, Ohm's law, which connects voltage, current, and resistance together. Thanks for watching. See you in the next video.